Thanks for your invitation to present this case story, Process Development for Production of Tier 3 Ultra-Low Sulfur Gasoline, Bringing an Old Process into the 21st Century. The presentation is in three parts: the business case, studying the detailed chemistry of the process, and commercial field tests. For the business case, we need to talk about two things, which are gasoline sulfur and octane. Gasoline sulfur reduction toward 10 ppm has been slow in North America. And this chart shows the U.S. average ppm sulfur in gasoline. It has been going down at about 2 ppm per year, approaching 10 ppm in 2020, which is the EPA's Tier 3 requirement. And this leaves a gap of 14 ppm from 24 to 10 that needs to be filled in order to meet the Tier 3 requirement. And I would point out that we are currently in the middle of 2018, which is halfway through this time gap, so a lot is going to happen in the next 18 months. Now, octane. Gasoline desulfurization causes octane loss. As this gap is filled down to 10 ppm over the next 18 months, octane will be destroyed for reasons that I will explain. This is going to be a significant contraction in the octane supply capacity of North American refineries. Now, what has been happening with octane? I snapped these pictures yesterday in Wheaton, Illinois. The differential is $1 a gallon between 87 octane regular, 318 per gallon, and 93 octane, 418 per gallon. This is bigger than we've been accustomed to historically. Here is the chart of octane demand and price continuing to rise. This is a chart in dollars per gallon. The U.S. premium minus regular retail price differential, what you see at the pump, for the last 20 years, and it was stable at about 10 cents a gallon for a long time, and then it started increasing in 2005 and has been going up ever since. This chart ends at 2016. The average in the US was 50 cents per gallon. So we have a totally different picture on octane demand and price than has historically been the case. So we have been saying for the last 3 years that an octane sulfur squeeze is coming. And that's because we have this gap to fill from 24 ppm down to 10 ppm over the next 18 months. This will result in octane destruction, a reduction in octane supply capacity in the United States. Meanwhile, octane demand and octane price are increasing, and this is the picture for an octane sulfur price squeeze. Those who are able to produce ultra-low sulfur gasoline with minimum octane loss are going to have a big competitive advantage in the North American market. That's the business case. Now we're going to spend most of the rest of this time talking about studying the detailed chemistry of post-treating. And I have to begin by telling you about post-treating. The first point is that 98% of gasoline sulfur in the United States comes from fluid catalytic cracker gasoline. So clearly this stream, fluid catalytic cracker FCC gasoline, is where we need to focus attention for sulfur reduction. Now here is a simplified block diagram of a chunk of the refinery showing sulfur reduction in the FCC process train. We have feedstock that has 20,000 ppm sulfur, goes to a pretreater that is a desulfurizer. It reduces the sulfur in the feed to 5,000 ppm and also improves the crackability of the feed. The cat cracker cracks the feed and makes gasoline that is 250 ppm sulfur, which goes to a post-treater to bring that 250 down to 75 ppm sulfur in the post-treated FCC gasoline, which is what we need in order to blend that with sulfur-free blend stocks to get the total gasoline pool down to 30 ppm. Now the post-treater is where our process development is focused. And that's because FCC gasoline post-treating destroys octane for reasons that I will explain shortly. Now there's one more piece that we need to cover here as background, and that's octane versus chemistry. So these are charts of RON, which is research octane number versus carbon number on the left, and MON, motor octane number versus carbon number on the right. And we're going to look at the RON chart. The lower curve is for normal paraffins, and it shows that normal paraffins are low in octane number, and the octane of normal paraffins gets lower as the carbon number of the normal paraffin gets larger. Now on the other extreme we have the purple curve, which is aromatics. They're all good for octane regardless of carbon number, and the same pretty much for olefins. They're all good for octane. The reason we destroy octane in the post-treater is because we saturate olefins on the upper blue curve to make paraffins, which are terrible for octane. And this is a side reaction that occurs while we're removing sulfur from the organic sulfur compounds that we need to desulfurize. So it's an undesirable but inevitable side reaction that you saturate olefins to make paraffins, and that's why octane goes down. Now we're ready to talk about pilot plant testing. These are the pilot plants we use for all our work. They're at a company called C Solutions in Thessaloniki, Greece. And these kind of pilot plants are the ones that are the best for doing this kind of process development work in refining. Now here is a chart of pilot plant data. We call this the performance curve. It's a chart of olefins in gasoline on the vertical axis, product sulfur on the horizontal axis. As we go from right to left on this chart, we are increasing reaction severity in the post-treater in order to reduce the product sulfur. And as we do that, as the three data points show, olefins go down because of the side reactions that saturate olefins. And in this particular set of data, we're using reactor temperature as our process variable to increase severity. At the cold temperature, you see we have about 80 ppm sulfur and about 23 weight percent olefins. At the hot temperature, we're down to 20 ppm sulfur and 18 weight percent olefins. So we learn the shape of this curve when we increase temperature on this particular feed. Now, a thing that we're interested in particular is what happens to this curve as we further increase severity to go deeper in desulfurization. And here we see the same data. The three green diamonds are the same data points, except here we are charting the RON octane on the vertical axis instead of olefin content. The two correlate with each other. And so going from right to left, we have cold, warm, and hot reactor temperature. And then we have three white data points. These are for a more active catalyst. The same three temperatures going from right to left, cold, warm, hot. And these white data points are shifted to the left because the more active catalyst gives us more kinetic capacity, and we get lower product sulfur with the same range of temperature. And you can see here when we went with the more active catalyst and the higher temperature, we got down to single-digit ppm sulfur, but the octane loss accelerated greatly. Now, and we have quite a lot of other data now like this, but when we first saw this data in 2015, it was the first time that we or any of our clients had actually seen data on what happens when you take this process and increase the severity to get down much deeper in desulfurization. And it turns out that the octane loss that occurs when you do that is much greater than the industry has been expecting. The industry expectation was that Tier 3 sulfur would cause a loss of about a half octane. And suffice it to say, with the data that we have from both pilot plant and commercial data, the octane loss is much greater than that when you actually measure it. Now, I'm going to leave this chart up a minute while I give a pop quiz, just a quiz question. And this is a question that if you have a high school chemistry student in your family, you might want to have them take it and see if their teacher or anyone in the class knows the answer to this interesting question. How many different chemical compounds are in gasoline? And the answer is about 450. And we know that because we have analyzed 70 plus gasoline samples with a very detailed analysis that identifies every compound in the gasoline. And a typical gasoline will have 450 different compounds. The number of compounds that we have found in gasoline across the full range that we've analyzed is 759. So we have a grid of 759 rows, and the columns are the different samples, and we have in there the composition of all of the gasolines, the feeds and products from our pilot plants, commercial tests, and other gasoline samples. And this data has greatly increased our understanding of what's happening in this process and our ability to help refiners decide what to do to meet the 10 ppm sulfur specification more profitably. For example, one thing that's useful is look at the performance curve for compound groups. C5 olefins on the left, this is what happens to the group of C5 olefins, and we see that that performance curve is quite steep. On the right, the C9 olefins, the curve is much flatter. This shows a general trend, which is that the lighter olefins are more reactive in this process, and so feeds that contain more light olefins are going to be more susceptible to octane loss. And we need not restrict ourselves to compound groups like this. In fact, we can look at individual compounds and what happens to them as we increase severity. So here we have 2-methyl-2-butene. We know the slope of that curve, and it turns out that's a particularly important compound in this process. And on the right, we have a C10 olefin that has a strange performance curve. It's opposite in direction to all the others, meaning this is a C10 olefin that is being formed as we increase severity. That's off the radar screen. We don't normally think about any olefins being formed in this process, but we believe this is something that is real and significant for this process, and that you learn when you use detailed analysis. Finally, we are chemical engineers here. We must address the question of how are we going to apply this in the real world. And commercial field tests is the way we have brought this to the refining industry. We are using our 759 compound analysis, which we refer to as a blood test, to help refiners see what is happening on each of their actual units, and then combining that with all the information we developed in this 3-year project to help them improve their Tier 3 sulfur strategy and the profitability of their Tier 3 sulfur strategy. So here is an example of a blood test run on a commercial unit. Feed is the gray curve. Product is the orange curve. We're charting weight percent olefins versus carbon number here. And so we see on the gray curve for the feed The olefins are concentrated in the C6, C7 area. And we see on the orange curve that the olefins are being converted across the boiling range. The total olefin conversion is 51% in this case, which is 7 ron octane loss, much higher than what this refiner expected. And as a matter of fact, this refiner has decided to make capital investments to reduce this octane loss. Now here's a different commercial post-treater, the gray curve for the feed and the orange for the product. We see here this feed, the olefins are much more heavily concentrated in the C5 olefins and C6s, and there is very little conversion of the light olefins in this unit because the unit is designed specifically to avoid saturating the C5 olefins and losing that octane. Still, this unit experiences 25% olefin conversion because of saturation of higher molecular weight olefins and 2 ron octane loss, and those will increase when they go deeper in desulfurization. And here is a third example from a third commercial unit, 30% olefin conversion, 3 ron octane loss. So this is a very simple and effective way to analyze a commercial unit. We just get a sample and analyze it in this way. It tells us what is happening in the unit in detail and what allows us to predict what will happen when you go deeper in desulfurization and estimate the effects of different steps that can be taken to improve octane sulfur performance. We've done this on many commercial units in North America. This 3-year process development program that I have described has resulted in a database and models that are helping our clients decide Tier 3 gasoline strategy, decide capital investment strategy, decide process design, catalysts and licensors, decide gasoline production strategy, and something I didn't have time to discuss that is important is deciding sulfur credit strategy. And we have several cases where this information has resulted in refiners deciding to invest new capital, which is really what is needed. Conclusions. Our business case tells us an octane sulfur squeeze is coming. Our pilot plant data and models developed from them tell us that octane loss will be more than is anticipated. And our commercial field tests tell us that capital investments are needed to mitigate octane loss. Thanks to AICHE for inviting me to your meeting today, and thanks a lot for your attention. And I encourage anyone who is interested in this topic to please contact me anytime. All of our work is multi-client. None of it is proprietary. All of it is available to anyone at a small fraction of its cost. And I've shown you only a little bit of what we have. We're happy to discuss more details with anyone at any time.